All right, so let's look at some z-score problems just real quick before we get into today's stuff. The main idea with the z-score is it's how many standard deviations an x value is away from the average. So z-scores are how far x is from the mean in terms of standard deviations. That's all a z-score is. If you have a z-score of, let's say, 2, that's telling you that you are 2 sigma above the mean. That's all it means. So if you have a z-score of 2, you're 2 standard deviations above the average. So suppose your professor records scores on a test using z-scores. If you got a score of 2.2, explain what this means about your test score. And I think I might have gone over this problem now that I'm looking at it, but we can just talk about it real quick. This just means you're 2.2 standard deviations above the average. So you did pretty well on that test. You are 2.2 standard deviations above average. You're doing pretty well. Number 3, a baby's weight is said to have a z-score of negative 1.88. So that's 1.88 deviations below the mean. This is a pretty small baby. Like this would be a tiny child. Let me keep going. Number 4, weights of prize steers are said to be approximately normal. That's going to be an important term from now on. We talked about the normal curve with a mean of 1,152 pounds. My goodness. And a standard deviation of 84 pounds. Wants to know what the actual weight of a steer is if they have a z-score of negative 1.5. So the first thing you should recognize is this is going to be less than average because it's a negative z-score. It's going to be 1.5 deviations below the mean. I'm going to use our formula, z is equal to x minus mu over sigma. And we say our z-score is negative 1.5. We don't know what the steer's weight is, so that's x, which is unknown, minus the average, 1,152, over the standard deviation, 84. I'm literally just plugging in the information from the problem into our equation. This is about as intense as algebra will get in this class, solving this problem. There won't be any more algebraic steps than maybe 2 or 3 in this class. So the first step we'll do is multiply both sides by 84. That's going to cancel out that denominator of 84. Very basic 2-3 step algebra problems here. And then to get our old calculadora, we say 84 times negative 1.5 would be negative 126 is equal to x minus 1152. After we multiply both sides by the 84. Then we're just going to add 1,152 to both sides. And it turns out that x is equal to 1,026 pounds. And we did get something that was below average because it was negative 1.5 z-score. So we basically just took away 84 pounds and then a half of that because it is 1.5 deviations, this guy right here, below the average. There's really not too much else to z-scores. This is it. Let me see if there's any other ones we can maybe look at. Let's look at number 7 real quick, and then we'll move on to the empirical rule. Town's high temperatures in December have an average of 36 degrees, standard deviation of 10 degrees. In July, the same town has a mean of 74 and a standard deviation of 8. In which month is a 55-degree temperature more likely? So when you have 2 different populations and you want to see which one has a higher chance of getting this value, what we can do is find the z-scores from December and the z-score for, what was it, July. So we want to know what is the z-score to get 55 degrees in December, where the average is 36 and the standard deviation is 10. So we're going to figure out what this z-score is. So that's going to be 55 minus 36 divided by 10. So in December, getting a temperature of 55 degrees is nearly 2 deviations above the mean. It's 1.9. So it's 2 or so standard deviations above the average. In July, 55 degrees minus 74 over 8. So we're going to do 55 minus 74 divided by 8 is negative 2.375. It is more than 2 deviations below the mean. So it turns out it's far more likely to occur in December because it's closer to the average, relatively. That's a really important thing. 55 being closer to 74 or 36 is not really what we're asking. We're asking in terms of these deviations, how far away is it? And in December, it's closer in terms of deviations than it is in July. So whenever you're given two populations and you're asked to compare the likelihood of getting some outcome, you're going to look at these z-scores, like we did right there. All right, that's about it for z-scores. There's not much to it. It really is just that formula over and over again. You might be solving for different parts of it, but it's just that formula. And also the interpretation. Z-scores are the number of deviations above or below the standard deviation. All right, so next up, we're going to be talking about the empirical rule. And there is a calculator thing we can do, and I'll show you it very briefly. But the main idea of the empirical rule is that these are fixed percentages. So let me zoom in, extreme close-up right there. If you have a normal curve, then 68% approximately of your data will be between 1 deviation below the mean and 1 deviation above the mean. 95% of your data will be within 2 deviations of the mean. So if you add 2 sigma or add 2s and then subtract 2 sigma or 2s, depending on if you're talking about population or sample. So that's 95%. And then 99.7% will be within 3 standard deviations of the average. And these are fixed. This is called the empirical rule. This is a rule, so it's not going to change. These percentages are fixed. So if you had, like as an example, I'm just going to scroll over here. If I told you the average height of males at this school is 70 inches tall, I have no idea if that's true. But if the average height of males is 70 inches tall, and let's say that the standard deviation is 5 inches. What that's telling you, if we go 1 deviation above and 1 deviation below, 68% of the males at this school, 68%, are between 65 inches tall and 75 inches tall. That is the empirical rule. And so it's worth maybe writing these down or keeping this page handy. These percentages right here are fixed. These are approximations, so these are not the exact value, but these are close enough. This is what we use for our empirical rule. So going through these really quickly, it says approximately 68% of observations are within 1 standard deviation. I almost messed up the empirical rule. 1 standard deviation of the mean. 95% of observations are within 2 standard deviations of the mean. And 99.7%, almost everybody, is within 3 standard deviations of the mean. It is very rare to ever see anybody more or less than 3 standard deviations above or below the mean. Those are your Yao Mings, and I'm trying to think of anybody else that's like incredibly tall or incredibly short. Peter Dinklage, he'd probably be around like here-ish. So actually, no, he's probably not. Peter Dinklage is probably like right about there. Who's the guy that played Mini-Me? Don't remember. But that guy, he's very short, or he was very short. All right, so let's look at some problems for these empirical rules. Yes, I was just trying to remember. Yeah, sorry, I was trying to remember who the guy was that played Mini-Me in Austin Powers. And the name's going to come to me in like an hour or two, and it's going to make no sense in context when I tell the kids that that's his name. Probably didn't make too much sense right now, but Yao Ming over here, and then whoever played Mini-Me over here. Okay, so the height plane of senior high school students is approximately, I should have just read ahead, this is the same kind of problem. So there's 71 is the average, and the standard deviation is 2.5 inches. So they don't have as much variability as my made up problem up here. So it says label the normal curve, so we've done that. Maybe we could put inches and inches. If we wanted to, we could figure out these values too, so let's go ahead and do that. So one deviation to the right is going to be 73.5. Two standard deviations away, so we're going to add another standard deviation, is going to be 76 inches, and then 78.5. I'm literally just adding sigma, our standard deviations, each time I go one more to the right. So this is plus one standard deviation, plus another, and then plus a third. We can also take away 2.5 inches from 71, and that'll give us 69.5, and then that'll give us 67, I think, and then 65.5. I'm going to verify those because I'm scared that I made a mistake. So 71 minus 2.5, 68.5. Yep, absolutely didn't make a mistake. And then that answer minus 2.5. Yeah, no, this was all wrong. That's great. At least it's not being recorded. So it should have been 68.5 for this one. We can do a little bit of surgery right there, and no one will ever be able to tell. And then we have 66 instead of 67. This is going to be a little bit more difficult, but if we use our imagination, it's going to be a 66. And then 63.5 is actually going to be not too bad because a 5 kind of turned into a 3. There we go. Perfect. Okay, so it says, what percent of the male students are shorter than 66 inches? So what you need to do is find 66, which was this guy right here, and figure out what this area is to the left. And I'm trying to think of how I want to do this. If I have any lead in this pencil, I think a pencil is going to be best. So we want to figure out this area. And it's always going to be based off of the 68, 95, or 99.7. Like you're going to use these to help you get this answer. So what I might point out is that this middle area, 2 deviations away, is 95% approximately. So these 2 deviations away is 95%. And what that's telling us is the area in the tails. Remember, this has to add up to 100%. 100% is what the total always will be for basically anything. The total has to be 100%. So if the middle is 95%, we can figure out what these 2 tails are by taking 100%, so 1 minus 95%, so 0.05. You could also say 100 minus 95. You can deal with percentages or decimal percentages. It really doesn't matter too much, whichever one makes more sense to you. Either way, there's a total of 5% left over if the middle's 95%, and hopefully that makes sense. The middle's 95, so there's 5% left over. And what we're going to do is divide that by 2 to figure out that there is 2.5% here and 2.5% here, which is telling you the percent that is less than 66 inches, which is what this is right there, is 2.5%. So the probability that x is less than 66, where x is the height of these like random male, is 2.5%. X is equal to height of random male. So the chance of being less than 66 inches tall, apparently, according to this distribution, centered at 71, is 2.5 inches. All right. I'm going to erase these markings here so I can do the next one. So I'll erase that 2.5, erase this, erase that, 95%, and erase this. All All right, next one says they want to figure out what percent are taller than 73.5 inches. So that's going to be asking for this area. And so again, we can use our knowledge of this empirical rule. It's going to always be based off of these values here. Every single time for the empirical rule, when you have a normal curve, it'll be based off of these for this unit. So what I might do is use that middle 68% this time. So this is 68% of the data. I want you guys to see if you can figure out what these two tails have to be, and then see if you can get what this answer will be. I'll give you, like, I don't know, 30 seconds. So hopefully what you're doing is 100% minus 68%, which is 32%. You then got 16% for each of the tails. So this is 16 over here. This is 16 over here. And that makes sense because these all add up to be 100%. So 16% in this little tail, 68 in the middle, and 16 more. So the answer over here is 16%. And really, it's approximately 16%. So if you wanted to, you guys can put little squiggles right there. But I'm fine with putting an equal sign there too. Got a couple more. Let's look at those. Just kind of scooch this on up a little bit. So the next one wants us to figure out the chance of being between 66 and 73.5. Now, what I'm going to do on here is I'm going to redraw this because this is starting to get a little bit messy, and that's going to be easier just to redraw it. I'm not going to put all the values though. I'm just going to put the values I care about. So 66 inches is going to be 2 deviations to the left. So it'll be right about there. That's 66. And 73.5 is 1 deviation to the right. If we're centered at 71, like this. So this time, we want to find this area, the chance of being between 66 and 73.5. And then what you'll hopefully start recognizing is you can use past answers to help you. We already found out that this was 16% earlier. That 16% is greater than 73.5. And we found out that this was 2.5%. From the part A. So we're just going to take 100% and subtract 2 percentages, 2.5% and subtract 16%, because we want to find that middle value. So let's do 100 minus 2.5 minus 16. So it's 81.5. And so it's telling us that the probability that our height of a random person, or height of the people, is going to be, the probability of being between these is apparently 81.5%. Hopefully, you're like, there's nothing too bad. I kind of like these problems. They're like little puzzles. There's 3 fixed rules, and you just kind of keep using those puzzles. Let's do maybe one more, and then I feel like you probably get the gist of it, and then we'll call it on the lesson part, and then we can start working on homework. So shorter than 76 inches. So this one, I feel like we can do pretty quickly. 76 is right here. So let me draw a curve. Want to get shorter than 76, so I draw this curve. I really do recommend drawing the curve and shading it in like this, I feel like it helps a ton. We found out earlier that this was 2.5% of the data. And so it's going to be pretty easy to figure out what that shaded region is. We're just going to take away 2.5% from 100, which I was going to try and do in my head, but I seem to not be sinking any balls today into the net. So I'm going to instead use my calculator. Probability of being less than 76 is 97.5%. And this is like the last major thing for the unit besides percentiles, but percentiles are really related to what we're just doing here. So z-scores is what we learned on Friday, and the empirical rule is what we're learning today. I'm just gonna do more practice of it. I'm going to call that on the video. Hopefully I was recording. I was. Fantastic.